All right. So today we will start with the second part of fourth unit, and that is the Mosfet. Now, first of all, let me show you the entire transistor family so that can be. Uh, you don't have any confusion with that. So the transistor, we have already seen the transistor semiconductor devices. So it is basically divided into BJT and field effect transistors or field effect devices. Okay. So the basic difference is that BJT is operating, rather is current control device, FET is voltage control device. In BJT, we have NPN and we have PNP device. Okay. In FET, we have JFET basically, and this JFET is again N channel and P channel. Okay. Now another branch of this field effect devices is the Mosfet. Mosfet stands for M stands for metal oxide semiconductor field effect transistor. Okay. So we have metal oxide semiconductor field effect transistor. So it is again belonging to the class of field effect device, but it is metal oxide semiconductor. This is basically the structure which is making it different than the FET, the JFET that we have already seen. Okay. Now, if you remember, in junction field effect transistors, we had physical junctions, P and N junctions between the channel and the gate. Okay. That junction is not existing in this MOSFET device. So in MOSFET device, there are again different classes. We have the depletion MOSFET and we have the enhancement MOSFET. Okay, and each of them will be having different, again, N, N channel and P channel and so on and so forth. So again, you have these variants. Okay, let us see the construction of the depletion type MOSFET. We'll start with the depletion type MOSFET, and then we will see its characteristics, its construction, working characteristics, and go on to enhancement MOSFET. Okay, so the very first thing that we'll do is the depletion type MOSFET. It is also called as D MOSFET.
So your screen is stuck.
Hello.
Yes, sir. Now
Yes,
it is
sir.
visible.
Okay. So again, let us see the construction. For that, I'll have to fetch the picture. So this is the depletion type MOSFET construction. So very curious kind of construction we have. So what do we have? A slab of P-type material is formed from a silicon base and is called a substrate. So you have this P-type slab which is formed first of all. Okay, so we have a P-type bar or let us say region P-type substrate. It is called as a substrate. All right. Now this is connected to the external world by or connector by metallic contact. So you have these metallic contacts here. So you have this metal and then you have these contacts over here like this. And this p-type is called as a substrate. It is also called as a body of the transistor. Okay. Sometimes this substrate is internally connected to the source terminal. Okay. Sometimes you have this. So many times you will see that there are 3-terminal MOSFETs and there are 4-terminal MOSFETs also. Okay. So now what you're looking at is a 4-terminal device. You have the usual convention, drain, gate, source, and then you have an additional connection called as substrate or body. Many times, as I said, many times substrate and or the body and the source, they are internally connected. So external, you get only 3 terminals for the device. So it becomes a 3-terminal MOSFET. Okay. Now, which of these are types are 3-terminal and 4-terminal? The discrete devices. Now, do you know the difference between discrete and integrated? Guys, what do you mean
So
by discrete?
pardon.
What do you mean by discrete and what do you mean by integrated? Discrete
So
devices are separate devices. Only one type of device that you see, a transistor or a diode. All those are discrete devices. You must have we've already seen the pictures of such devices, right?
yes, sir.
Whereas, as opposed, those are called as the discrete devices, as opposed to the ones which are integrated on an integrated circuit. So you have a monolithic structure where so many different transistors, so many different components are manufactured on the same silicon wafer. Okay, that is the reason why we have two different types of devices, and that is one is called as a discrete device and the other one is called as an integrated device. So in most of the discrete devices, you get these 4-terminal variants. Okay.
So this MOSFET is a discrete device or integrated
It
device?
can also be integrated. See, bipolar, all the transistors that we have seen, they can be either discrete or they can also be integrated. Both.
Yes, sir.
Okay. And in such cases, there is a reason why we have this thing. So we get a 4-terminal device in this case. The source and the drain terminals are connected through the metallic contacts. As you can see, the source and the drain, they are connected again. So this color, call it as red color or whatever. So this is actually a metallic contact. It's a metal. Okay, it doesn't play any part except for connecting it to the respective region. So this drain terminal is connected to this block, source is connected to this block, and gate is connected. You can see it is just connected to something over here. We are going to see what it is. So the source and the drain terminals are connected through metallic contacts. To what? To an N doped, okay, N doped region. So we have an N doped region, and this N doped region is these two regions are actually connected by another N type region. So this is a very peculiar construction. So we have this N type doping here, N type doping here, and this channel also is created by N type. So we have all this region as N type. Okay, this you have P type, this you have N type. Okay, gate is connected to a metal contact surface, but it is insulated from the N channel. As you can see, this is a layer of silicon dioxide, which is actually an insulator. All right. So you have this metal, you have this oxide, and you have this semiconductor. That is where it gets the name from. MOS, metal oxide semiconductor. All right. This
Yes, sir.
silicon dioxide layer is very, very thin. Okay. So SiO2 is an insulator which is called as a dielectric. Called as dielectric. Okay. Now, once we have such a kind of structure, if you remember the basic device, you have two conductors separated by an insulating material. What does this give you? Two conductors separated by an insulating material. What type of device is this? What is this device?
Capacitor.
It's a capacitor.
Capacitor.
So necessarily this also forms a capacitance. Okay. So the gate, silicon dioxide, and this semiconductor. So you have some capacitance over there. And capacitance means what? What do we say when we say capacitance? What do we have? We have the electric fields which are set up, isn't it? Do you remember the basic discussion that we had? Electric field is set up.
सर ये डाइलेक्ट्रिक का मतलब क्या हुआ यहाँ पे?
ये इंसुलेटर को भी डाइलेक्ट्रिक भी बोलते हैं.
Okay, sir.
It is a special type of insulator and it is called as dielectric. जैसे capacitance में if you see, we already said dielectric constant. Okay, so you have
सर किस टाइप का मतलब इंसुलेटर एज इन की इसका प्रॉपर्टीज कैसा होगा?
silicon dioxide. It is made up of silicon dioxide and it is an insulator, basically dielectric. And you'll see that this dielectric constant K.
all dielectric materials are made up of only silicon dioxide.
What?
सर मतलब डाइलेक्ट्रिक जहाँ पे भी आएगा वहाँ पे
नहीं. Dielectric materials can be different. Dielectrics can be manufactured with different types of materials.
सर मतलब जैसे कि उसका कुछ प्रॉपर्टीज या फिर कुछ उसका मिक्सचर वगैरह कुछ होगा ना?
उसमें क्यों जाने का है? Why to go into that? We have this silicon dioxide itself as the dielectric. For silicon dioxide, dielectric properties refer to somewhere else. My intention here is why basically the construction of the device itself. So क्यों ये पूछना चाहिए था, क्यों SiO2? SiO2 क्या है, उसके प्रॉपर्टीज क्या है, ये बाद में आएगा. ये पूछना चाहिए why SiO2? So SiO2 क्यों? The reason is very simple and obvious that you have a semiconductor here which is silicon. और silicon के ऊपर we can easily create an oxide layer. दूसरा मटेरियल उधर जाएगा ही नहीं. It will be very difficult for us to manufacture.
So you are not audible.
Okay?
बीच में
सर आपकी
डिस्कनेक्ट हो
आवाज
गए
कट
थे.
गई थी.
What I am saying is why silicon dioxide should be the question. So it is easier for us to grow the silicon layer on the top of this semiconductor, which is itself silicon. So it is easier for us to grow the layer. Oxidation बहुत easy होता है उसका, and that is the reason why we have been using silicon dioxide as the dielectric. ठीक है? Important point to note over here is that there is no direct electrical connection between the gate terminal and the channel. So there is no direct electrical connection. See that it is separated or insulated by this dielectric layer, which is silicon dioxide. So gate this is the metal. You have the isolation here or insulation basically, and you have the N-type material over here. So there is no direct electrical connection between the gate terminal and the channel of the MOSFET. It is this insulating layer of SiO2 that accounts for a very high input impedance. The point to be noted here is why it is, how is it different than junction field effect transistor and bipolar transistor, तो और अलग बात है, लेकिन यहाँ पे करंट फ्लो होगा ही नहीं, गेट के अंदर करंट फ्लो होगा ही नहीं. Why?
So because
So there is
it is
no direct
insulated.
connection here. There is no direct connection over here. The only current that will flow for a very short duration of time till the electric field is set up. Okay, उसके बाद कुछ करंट फ्लो होगा ही नहीं. और अगर करंट फ्लो नहीं होता है, obviously what we have here is we normally apply the voltage here like this, whatever VGS. You have seen that. That is an input. So abhi some voltage is there and the current is almost zero. So what can I say about the input impedance? What can I say about the input impedance?
Sir, it is highest.
It is nearly infinite, nearly.
So,
But practically you have a very high input impedance, which actually is a good thing for a device. It is expected. All right. Now let us see the basic operation and characteristics of this type of. So first of all, understand the construction. Let us see the basic operation and characteristics.
substrate is made up of which material?
देखो क्या है, क्या लिखा है यहाँ पे?
Sir.
Obviously, it is also silicon, ना? It is P-type silicon. ये देखो, P-type silicon है ना? P-type semi substrate. So this is also silicon. This is also silicon. But this is P-type. This is N-type. समझ में आ रहा है?
Yes, sir.
Okay. Let us see the characteristics. Let me pull the figure again from. Just a moment, please. Okay. Now what we are going to do is we are going to connect it to the various sources, voltages. So I'm going to connect it like this. Gate and source I'm going to short. Okay. Substrate also I'm going to short it to the source. All right. Now the gate to source voltage here is set to 0. So VGS is set to 0. We start to analyze this. Let us call this as VDD. Okay. So if I apply VDD like this, what will happen? What do we see here? What do we see here? We see that you are applying voltage to this particular channel, which is a bar or piece of semiconductor N-type material. Now this N-type means यहाँ पे क्या होगा? Excess majority charge carriers क्या होगा?
Sir, electrons.
Electrons. So don't you think that the electron will start flowing if I apply external voltage between this terminal? So this terminal is positive and this terminal is negative. So electrons will start flowing towards what?
Towards a source terminal.
Towards the source. Electrons का charge क्या होता है? Negative. So they will be attracted
B.
towards this positive side, no?
Yes, sir.
So your electrons will start flowing in this direction, moving in this direction, like this. Okay? And the external current flow will be in what direction? That is your conventional current flow. It will be like this. Sorry. So your conventional current flow will be like this. ये हो गया conventional current flow का direction. So current is set up. Agreed to that? Do you agree to that?
Yes, sir.
Yes or no? अरे भाई
Yes, sir.
करंट होगा कि नहीं फ्लो होगा?
Yes, sir.
होगा सर.
होगा ना? तो ये ड्रेन करंट है, ये अपना ड्रेन करंट है. Now when VGS is equal to 0, we say that this ID is equal to IDSS. This is what we did last time also. I mean when we were studying junction field effect on this. तो इसको when VGS is equal to 0, जो करंट फ्लो होता है उसको बोलते हैं IDSS. ओके, यहाँ तक ठीक है? It's exactly like JFET. Now, when VGS is set at a negative voltage, say -1 volt, तब क्या होगा? Let us see. When VGS becomes -1 volt, तब क्या होगा देखते हैं. Let me pull the figure again. Substrate and source. Now इसके बीच में अगर नेगेटिव वोल्टेज यूज करो VGS which is -1 volt, तब क्या होने वाला है? So what will be the voltage at this gate over here? यहाँ पे क्या वोल्टेज होगा? नेगेटिव होगा ना? Guys, am I audible?
Yes, sir.
Yes, sir.
So this gate terminal is negative. So I can see that lot of electrons now. So these are all negative charges which will get accumulated on this plate. this metal gate, whatever. Okay, up to this point?
Yes, sir.
Okay. So the other side of this semiconductor, other side of this, क्या बोलते हैं इसको? डाइलेक्ट्रिक, वहां पे क्या सिचुएशन होगी? If now this side is negative,
Sir, holes will be accumulated.
or in other words, electrons over here will be repelled, है ना?
Yes, sir. Yes, sir.
यहाँ पे जब electrons थे, so if I just blow this figure up a little bit and just show you a very small part of that. जैसे कि ये so ये तो negative है, this is negative, so you have all electrons over here, I mean negative charges over here. अब यहाँ पे जो भी इलेक्ट्रॉन्स थे, पहले यहाँ पे जो भी इलेक्ट्रॉन्स थे, because of this influence, what will happen? They will start getting pushed. So ये इलेक्ट्रॉन्स जो है ये यहाँ पे पुश हो जाएंगे. They will be pushed away from the junction, away from this interface. Okay, and at the same time, now this is p type. So p type में majority क्या है?
So
Holes.
holes.
Holes. So these holes will start getting attracted here. समझ में आ रहा है?
Yes,
Yes,
sir.
sir.
So the negative potential at the gate will tend to push the electrons towards p-type substrate, okay, and attract holes from p-type substrate. Depending on this magnitude of the negative bias, which is the value of this VGS, a level of recombination between electrons and holes will occur. Okay, so ये electrons, ये देखो क्या हो रहा है यहाँ पे, ये electron है, ये hole है. So it is possible that they come across each other and they recombine. That also is possible. So they will recombine. So depending on the magnitude of the negative bias, that is your VGS, the level of recombination between electrons and holes will take place. Now, if recombination takes place, what will happen? What will happen to the total number of electrons in this channel? Yes. Suppose there were 100 electrons here. Okay, 100 electrons were there. And because of the application over here, say 50% or 50 electrons, they get recombined with 50 holes. So total number of electrons क्या होगा इधर? In that
Sir,
channel,
reduce.
the total number of electrons will reduce. And these are actually free electrons, don't forget that, which are available for, or rather which were available for conduction. So more the negative bias, higher will be the recombination. मैं इधर ज्यादा
Yes,
और
sir.
ज्यादा बायस देता हूँ इसको नेगेटिव, तो ये ज्यादा और ज्यादा इलेक्ट्रॉन्स पुश होंगे. They will try to go towards this p-type substrate. Holes from p-type substrate will get attracted towards here, and then there will be recombination. Recombination means that these electrons and hole pairs, where they were separated, now they are no longer separated. Electron will occupy that hole, and there won't be any more free electrons left for conduction. So the total number of electrons reduce if I increase VGS. So therefore, as VGS increases, remember increases means negative direction. What will happen to the drain current there? What will happen to drain current?
Sir,
Hello?
it will reduce.
Absolutely, it will reduce. Why? Because number of charge carriers are reduced. Electrons reduce हो गए यहाँ पे. So
Yes, sir.
similar to JFET, the drain current reduces to zero when VGS is equal to VP. So when a certain value VGS equal to VP, then the drain current reduces to zero.
So VP या VDSS?
VP, pinch off. We'll see more about
Yes,
that
sir.
when we see the characteristics, right? लेकिन जंक्शन फील्ड इफेक्ट ट्रांजिस्टर के लिए भी हमने पढ़ा है ना, पिंच ऑफ वोल्टेज क्या होता है.
Yes, sir.
Yes, yesterday we have seen that. So in fact it is some negative voltage. Okay, VGS समझो, VGS ऑफ बोलते हैं उसको,
Yes, sir.
और VGS थ्रेशोल्ड, VGST. ओके, ये डेटा शीट में दिया होता है. VP नहीं बोलते MOSFET में, बट टू मेक your understanding transition from JFET to MOSFET, I'm using these terminologies. So
Yes,
for
sir.
positive bias of VGS, now if you say अभी तक हमने VGS को negative करा, okay, for positive values of VGS क्या होगा. अभी समझो मैंने ये पॉजिटिव कर दिया, इंस्टेड ऑफ नेगेटिव ये मैंने पॉजिटिव बायस लगा दिया इधर.
Sir, ID will increase.
फिनोमेनन क्या होगा? These are positive, so it will
So
attract electrons, even major minority electrons from p-type base, p-type
yes, sir.
substrate. Okay, so minority electrons will be attracted into this particular n channel. So number of electrons in n channel will increase. Of course, ये minority में है तो ज़्यादा नहीं होगा, लेकिन there still will be addition of electrons, and so if for positive values of VGS, ID increases. Okay, and this ID increases quite rapidly. Let us see the
Yes, sir.
characteristics, then things will be easier for you to understand. So this is the basic working operation, or basic working principle of your okay. Okay. So now what you're looking at is both the transfer characteristics as well as the drain characteristics. I've combined it and put them side by side. तो ये क्या
Sir,
है
your
देखो,
screen is not visible.
screen is not visible again.
Yes,
सर
sir.
विजिबल है
Visible है ना?
Visible है, sir. Yes,
हाँ,
sir.
दिख
ठीक. Check your connection. Internet connection. Okay. So yeah, what are you looking at right now? You are looking at the characteristics.
Characteristics.
तो ये दोनों characteristics मैंने side by side लगाए. ये left hand side का characteristics है, that is a transfer characteristics. Just like your junction field effect transistor, it is your ID versus VGS. And your right hand side में है, what is it? It is ID versus VDS. So you can see that the characteristics are very, very similar to that of the junction field effect transistor. Acha, why this device is called as a depletion mode device? ये पता है? नहीं. Okay. So why it is called as depletion mode? Because as you go on increasing the negative bias for VGS, so if I increase VGS in the negative direction, what will happen to the electrons in the N channel? We've already said that. Yes?
डिक्रीज होंगे.
Electrons in N channel will
Sir, decreases.
decrease. Correct. Decrease, reduce because of the recombination. Okay. And when we have,
Yes, sir.
when we have, let us say, when there are no charge carriers, what do we call that? The region where there are no charge carriers, we call it as a depletion region. No.
Yes, sir.
So as if you are depleting the electrons from this region because of this type of bias. So it works on this principle. And that is the reason why it is called as a depletion mode or depletion MOSFET. It works on this principle. Now, as you can see in depletion mode, the characteristic take this particular form. So this green area is all the depletion mode. It means that your VGS is increasing negatively. But if I increase VGS in the positive direction, as I said, as we have already said, that the drain current increases. As you can see from this section here, the drain current increases. Okay, and it enters what is called as an enhancement mode. But anyways, we are not going to go into those details. But let it be known to you that this is called as the enhancement mode, the enhancement region or enhancement mode. Why it is called enhancement? Because what you are doing is, you are in this region, what you are doing is, you are actually increasing the number of electrons. You are attracting the number of electrons. ये positive हो गया, तो यहाँ से electrons attract होके number of electrons in the N channel is going to increase, and so it is enhancement of the charge carriers. That is the reason why this mode of this region is called as enhancement mode or enhancement region. And that also reflects in the output characteristics, as you can see very clearly over here. Okay. So at constant value of VGS equal to 0, if I increase VGS, you can see that ID increases rapidly, more or less just like exactly more, I mean like MOSFET, like JFET only. Okay. And then it saturates, the drain current saturates. Okay, even if you increase VDS, it won't increase any further. All right. ये समझ में आ रहा है क्या कैरेक्टरिस्टिक?
Yes, sir.
So at a constant value of VGS equal to 0, this is going to be the situation. Okay. If I decrease VGS, rather if I increase the VGS in negative direction, as you can see here, the drain current is less, becomes less and less, and it saturates at earlier point. It saturates at earlier point. Okay, and finally, this blue line is also a part of the characteristics. Now I'm drawing over with red part. This also is a part of characteristics. With at VGS equal to minus 6 volts, the drain current is literally zero, where it is cut off. Okay, so here actually VGS is equal to VP or VGS off. All right.
Yes, sir.
Okay. So this is the depletion MOSFET characteristics. Let
सर
us
इस
have a look at.
डिवाइस में ब्रेकडाउन रीजन नहीं होता?
होता है ना? I have not shown it, but it is of course going to be exactly the same as that of the generator.
Yes, sir.
Let us have a look at the symbols. So there are various confusing symbols, but let us use the one which is easier for us. I'm just going to show you all. So this is your drain, this is the gate, this is the source, and this is the fourth terminal, the substrate. This is for N channel. I will draw another alternate symbol for N channel. When we have three terminal device, you have this gate, drain and source. तो ये है N channel device. Similarly, we have symbols for P channel device. So this is for P channel. Just a moment.
Yes, sir.
All right. Am I audible?
Yes, sir.
Okay. So we have these as the symbols. If you look at the characteristics of the P channel depletion MOSFET, just let me fetch it once again. So this is the characteristics for P channel D MOSFET. As you can correctly guess, we have instead of that N channel, you have a P channel over there. So this is how it will be. Okay. The characteristics will be like this. All right, guys.
Yes, sir.
The next part is going to be very interesting. Why? Because it's the mostly used device, and that is the enhancement type MOSFET or E-MOSFET. Okay, so let us start with that. We'll just see the construction today, and more details we can go later. So enhancement type MOSFET, E-MOSFET it is called as. Now the basic construction is different than that of the D-MOSFET. Let me get the figure again. Okay, so what is the spot the difference?
Sir,
Whatever
the
is left.
N channel between N positive
Yes,
is
N channel. So there is no N channel. So there is no channel at all between the drain and the source. That is what it makes it different than your D MOSFET. So this is the construction
yes, sir.
of. So again, a slab of P-type material is formed from silicon base. That is this one, called as substrate. As with D MOSFET, substrate SS may be connected. So again, the same thing. SS may be connected internally to the source to create a 3-terminal device, or you may even have a 4-terminal device if SS is available separately. The source and drain are connected through metallic contacts, just like the D MOSFET. Major difference here is that there is no channel. This is the major difference. Again, your SiO2 layer, which is a dielectric, which isolates the metallic gate platform from the drain and the source. So we have this type of structure here. Let us see the basic operation. Please, we'll start with that. That has to be explained with a figure here. Okay. Now, first of all, understand one thing, that you have this N type here, you have this N type here, you have this P type here, and this P type, it's a it's a piece of semiconductor. So obviously, it will be having some resistance between these 2 points. हाँ क्या
Yes,
ना?
sir.
Yes, sir.
Semiconductor है, तो that is the reason why I've shown it as a resistor over there. There is no real resistor. This effect is shown as a resistance. Okay? So this is a resistance due to P-type substrate. We don't have a real resistor, huh? Please don't confuse that. I'm just showing the effect that this is a resistance effect, you can say. All right. Now again, as we start, when VGS equal to 0, as you can see, there is no voltage applied to the gate. Okay. Even if you want, you can short it also. There is no voltage applied. And voltage is applied between the drain and the source like this. Okay, what will happen? Will the current flow be there? Will the current start flowing? या ऐसे current flow होगा क्या?
No, sir.
No,
No, sir.
absolutely not. Absolutely not. Why? Because there is no path for the current flow.
Yes,
As
sir.
in case of our depletion MOSFET, there is no path, there is no channel over there. So current is not going to flow. So I can say that ID is equal to what? 0.
So 0.
Okay. Okay, somebody will say that there will be some electrons. P type है ना, तो P type में majority क्या है?
So holes.
Holes.
Minority क्या है?
Sir,
Obviously
electron.
Electron.
So electrons है यहाँ पे है ना?
Yes, sir.
Electrons नहीं है ऐसी बात नहीं है. Electrons है वो minority में है. ठीक है. और ये electrons they are distributed. I mean we don't have a channel over here. That is the reason why there is no current flow at all. When some positive voltage is applied to VDS, then things will change. And what will happen? Let us see. So when we apply some positive voltage between gate and source, VGS. So when VGS, some positive voltage is applied over here, what do you see? Or what do you think will happen?
Sir, all the scattered electrons
देखो
in
यहाँ
the P-type.
पे तो पहली बार यहाँ पे तो पॉजिटिव चार्ज सब क्रिएट होगा, है ना? जस्ट लाइक नेगेटिव चार्ज यहाँ पे पॉजिटिव चार्ज क्रिएट होगा बिकॉज ये पॉजिटिव है ना?
Yes, sir.
तो यहाँ पे अगर पॉजिटिव है तो दिस साइड will start attracting what?
Sir, electrons.
It will start attracting the electrons. So attraction, because of this attraction, what will happen to all these electrons? They will get attracted towards this interface. It is called as a interface, oxide interface. And so I have all the electrons lined up like this. जो भी इलेक्ट्रॉन्स है यहाँ पे लाइन अप हो जाएंगे बिकॉज ऑफ दिस पॉजिटिव VGS. ठीक है. All right. Actually speaking, when we have connection like this, when we have metallurgical connection like this, what is the very first thing that we have that I have not shown here? but if you look carefully, ये क्या है?
सर वो डिप्लीशन लेयर है जो जंक्शन पे
Correct.
बनता है.
So whenever we have a junction, whenever we have a junction, whenever we have metallurgical connection, we have a depletion layer which is formed at the junction. So ये जो color का जो layer है violet color का, that is the depletion region. So the depletion region will surround this particular structure. ठीक है? So let us put it down somewhere. So with some VDS positive, VGS at 0 and terminal SS directly connected to source, there are in fact two reverse biased PN junctions. Okay, so this is your N, this is your P. Okay, this is your N, this is your P. So there are two junctions which are reverse biased, you can see. Why are they reverse biased, by the way? Reverse bias क्यों है? To begin with.
Sir, because this one
Sir,
is
Because N
इससे
enhancement.
is
voltage,
connected to
sir,
positive,
sir
and
arrangement,
P is connected to negative, as you can see here. Okay. आया समझ में? So we have two
Yes, sir.
reverse bias PN junctions. Okay, even if this is not there, even if this is zero, and this source and the substrate both are at the same potential, it doesn't mean that it is forward bias, no? It is still reverse bias only. And depletion regions will be formed like this. Now, if both VDS and VGS are set to some positive voltages, just like in this case, what is going to happen? So it will make the source, the drain and the gate, sorry, the drain and the gate, both they will be positive with respect to source. So drain be positive hai or gate be positive hai with respect to source, as you can see. Okay.
Yes, sir.
This positive potential at gate will push the holes in the P substrate along the edge of this boundary. So as I have already said here, that the holes are pushed out. So the holes will be pushed out from here and electrons will be attracted in its place. Okay. So holes will be pushed out from that area which is along the edge of that SiO2 layer to leave the area and enter deeper into the P-type substrate region. Now what we get is a depletion region near SiO2 layer as holes are pushed away. But at the same time, so why this junction, why this channel is getting formed? That is what is important. So electrons are getting attracted, but holes are getting pushed out. Okay, so what we have is a layer of electrons accumulating here. तो ये लोकल एरिया अगर देखा जाए, ये लोकल एरिया अगर देखा जाए इतना ही, तो यहाँ पे मेजॉरिटी क्या होगा?
So electrons.
इलेक्ट्रॉन्स होगा ना?
Yes, sir.
Electrons होगा ना? तो can I say that we have converted that part of P type into N type? ऐसे बोल सकते हैं क्या?
Yes, sir.
Definitely. So SiO2 layer and its insulating quality will prevent these negative carriers from being absorbed at the gate terminal. So ये तो अंदर नहीं जा सकते ना, because there is a barrier. This SiO2 is there. It will prevent that these electrons from going anywhere else. As VGS increases in magnitude, the concentration of these electrons will increase. Okay. And what we essentially have is there is this N channel or this region, N channel is created, also called as induced. So N channel is induced over here. तो N channel अभी आपको मिल गया है. Alright. Now if I apply VDS, now is the drain current possible?
Yes, sir.
Yes, the drain current will happily start flowing like this. Why? Because electrons are available here. This is positive, this is negative. So what can we say is that after a certain value of VGS, after a certain value of VGS, which is actually called as threshold voltage, ID starts flowing. So as if यहाँ पे मैंने वोल्टेज अप्लाई किया तो ये डिवाइस ऑन हो गया. ID starts for flowing यानी ये ऑन हो गया. And this is actually what it makes it more interesting and more versatile than your DMOSFET. DMOSFET में हमको VGS निगेटिव करना पड़ता था, है ना, जीरो करना पड़ता था, निगेटिव करना पड़ता था. अभी यहाँ पे VGS क्या है? पॉजिटिव है. सो जैसे VGS में पॉजिटिव बढ़ाता हो at a certain value of threshold, after it crosses that threshold, drain current will start flowing.
So V threshold is nothing but a V off, no?
Exactly. लेकिन इस in this case, this V off is or VT is positive.
Yes, sir.
MOSFET, yeah, in MOSFET, and that also N channel, your VT is positive, and this is more sensible, no? Like मुझे निगेटिव नहीं करना पड़ता है उसको बंद करने के लिए, उसको चालू
Yes,
करने
sir.
के लिए मुझे पॉजिटिव करना पड़ता है. This is a very fundamental difference and very interesting one, because most of the times we have positive voltages with us, we don't have negative voltages with us. तो जीरो और पॉजिटिव के बीच में मैं खेल सकता हूँ, लेकिन जीरो और माइनस VGS ऑफ ये मुझे जनरेट करना पड़ेगा अदरवाइज. And that is the reason why these are mostly used devices as switches also. Okay, so we'll stop here for the time being. On Monday we'll resume this MOSFET and then go into the details of this. All right?
Yes, sir.
Achha, now I'll be giving you tomorrow. I'll be giving you the assignment for unit number 3, which we have completed. So, what about the assignment for unit number 1 and 2? Are you ready with those? It was given long back. Hello.
Sir, we only received one assignment.
2 assignments I have given. I clearly remember giving 2 assignments for unit 1 and unit 2. Check the group. I'll be giving you the 3rd assignment also. Okay? Okay, so we'll stop here.
Thank you, sir.